Can you hear me clearly?
Yes.
Okay, and my screen is shared. So thank you very much, and thank you for giving me the opportunity to give this talk, this meeting. The title of my talk is basically Minimizing the Effect of Manufacturing Uncertainty in MEMS Energy Harvester. This is mainly the work done by my former PhD student Hadi Medini, who is now a lecturer in College of Engineering, Swansea University, and it was carried out in collaboration with Professor Mike Friswell in the college as a second supervisor. So basically, what we want to talk today, if I can move to the next page, yes, that's basically an overview of my talk. So what you can see, I will give an introduction to uncertainty analysis, and the main reason for that because we want to talk about the manufacturing uncertainties. So I thought it's good to give kind of a brief introduction to the problem, and then I'll give again a brief introduction to mechanical systems known as MEMS. These devices, as you probably know, are very small. They are in milli or nano scales. And any experimental measurements on these devices is extremely expensive. And as a result, there are not many research which can provide us data, especially in terms of the uncertainty, to assess the uncertainty. I will give you two examples which I have found in the literature, which we have used the data from these papers for our case. And then we introduce a MEMS energy harvester with adjustable resonance frequency using electrostatic force, which is a concept that we have used in this device to minimize the effect of manufacturing uncertainties in these devices. So that's basically an overview of my talk. I started an introduction to uncertainty analysis, and I think the first important thing is to clarify what we mean by uncertainty analysis. I would use a little bit more or a broader word, which covers more cases. It's known as deterministic versus non-deterministic analysis. Obviously, with deterministic analysis is a process. It could be an experiment, but it could be an analytical modeling or numerical modeling. And what we say is the process is deterministic if you are confident about the parameters of the model, or if the model is chosen, you are confident the model is correct, and there is no uncertainty about the modeling. And basically, you can predict any outcome of that process modeling with 100% certainty. On the other hand, as we would expect, and it's obvious, is non-deterministic analysis, which is an analysis which is a lot of uncertainty associated. If it is, for example, an experiment, is the errors due to the experiment? Or if it is, for example, numerical modeling, errors related to the numerical modeling, or uncertainty about the parameters, the associated parameters that are basically exist in the process. So in the context of a multi-input, multi-output system, so if you consider like an energy harvesting device, we can basically simply model that as an input-output with the system, which your input is basically the vibration, for example, sources or other sources of energy from the environment. The system is basically the harvesting device that you have basically designed. And obviously, in the case of the energy harvesting, the output is the power that you would like to harvest from the environmental energy. This could be basically considered for any other discipline, so it's not limited to the energy harvesting, but we're talking about the energy harvesting problem. If you want to basically categorize this problem in different cases, and I believe that most of the talks that are given during these seminars is basically one of these categories that I have basically simply sketched out here, is non-deterministic problem when the input of the system is known, and when the system that you have designed, everything is completely known and certain, we call it deterministic. And then what we're interested is simply to calculate the output. And that's basically can be called deterministic forward problem. If the input system is known and the output is known, but we have a prior knowledge of the system, some parameters of the system, we have some initial guess, but we can basically use the known input and output, but they are deterministic, to estimate or parameters of the system. That is known in the literature as modal updating. If the system is completely unknown, similarly the output and the input are known, then that is called the system identification. It also can be categorized in the case of the design, when you want to design the system. If the input is non-deterministic, the system is known, we can say that is a random analysis. It's basically random vibration that we are familiar with. And the one that I'm going to talk today mainly is when the system input is known and is deterministic. So we assume we know exactly how much energy and we can model it exactly in the system. But what is unknown is the system parameters of the system, which are not deterministic. We cannot assign a single value to the parameters of the system due to the reasons that I will explain later. And in this case, when you do basically the calculations, you would expect the unknown to be non-deterministic. And this is called uncertainty propagation, or it's a forward problem, but it's called uncertainty propagation. And that is the topic that I'm going to talk today in the energy harvesting context. And obviously, there is another set of problems in this field. It's known as uncertainty identification, the stochastic model of everything. It's basically when the system is non-deterministic and incorrect, and you use the non-deterministic outputs to identify the non-deterministic parameters of the system. But that is not the subject of today's, mainly this uncertainty propagation or forward problem that we're going to talk. Okay, so having that in mind, this is known as a non-deterministic analysis, right? Because the system is uncertain. There are different things in the system that could be uncertain. In the literature of the uncertainty, the whole uncertain analysis or all type of the uncertainties can be categorized into two groups, known as epistemic uncertainty and aleatory uncertainty. So what is epistemic uncertainty? Anything related to the lack of knowledge. So for example, you have a model, you model it as a linear system, but it's actually in the physics, it is a non-linear system. Any errors in the measurements, like measurement noise, or human errors, for example, lack of skills, or for example, if you use some fitting methods, errors due to discretization, numerical discretizations in finite elements, lots of other types of errors can be categorized as epistemic uncertainty. And what we can say in an ideal world, this type of uncertainty is generally reducible. We can reduce them by basically gaining knowledge of the physics, or if we can improve our experimental facilities. And theoretically, not in real world, we can say one day we can reduce this epistemic uncertainty to zero, although this could infinity may not happen, but in theory we can assume epistemic uncertainty will happen one day. So on the other hand, the statisticians have known another type of uncertainty, which is not aleatory uncertainty. This is mainly variability in the system parameters. So example of that is you assume it's a test structure variability, which could arise from variability in the structural parameters such as thickness, material properties, and or joint parameters. So I'll explain this later, what we can consider as an aleatory uncertainty in the energy harvesting context, but it's mainly the system parameters which could be considered as aleatory. So as I said, our talk today is mainly on this type of uncertainty, which is aleatory uncertainty. So if we say, okay, there is variation in the system parameters, so the parameters of the system are not certain, and we can only assign a range of parameters on the system. As I said, the example is, imagine you have designed an energy harvesting system, and you have assigned some parameters to that energy harvesting system. But when you send this to the manufacturer, you give them a nominal value, which we can say that is normally what we call the mean of those design. But when they manufacture this device, and when they produce a large number of these products, they basically can't end up with a variation in the parameters. This could be either due to the geometric parameters, which nowadays they can be controlled very well, but it also could be related to the assembling process. So if you assume, for example, Airbus make 100 aircrafts, all have to be identical, and they have been designed to be identical, but you won't expect that they are going to be really identical, because even in the assembly process, the stiffness of the joints, the damping in the joints could be changing due to the assembling process. So that's what we call this aleatory uncertainty, because it's something coming from a manufacturing process. There is no way that we can reduce that, right? So it's, when it comes to the modeling, we have to physically model this as an aleatory uncertainty, because it's a variation which exists in the physics of the problem. It's not a variation due to the error, which is referred to the epistemic uncertainty. In the statistical community, obviously there are two types of methods that we can model these variations, known as probabilistic methods, that normally you assume a PDF. The well-known one is Gaussian, lots of other types. But it normally works well when you have a large number of data. And if you imagine we want to gather data from industry, it's always not feasible to have a large number of data. And the challenge here is, what with not having enough data, the PDF that we estimate based on small number of data will not be accurate. So on the other hand, in recent years, non-probabilistic methods have been emerged, and there are lots of focus on this field. And the main reason is these non-probabilistic methods is only looking at the range of the parameters. So, for example, it's very easy to go to industry, ask an Airbus engineer, what do you think is going to be the range of these variations in this, for example, in thickness of this thin plate or anything like that. They can give you an upper and lower range based on their experience, or what we call expert knowledge. But if once you ask them about the PDF, it doesn't go anywhere. They don't understand what PDFs are. So that's why there are lots of methods recently emerged called methods like interval modeling, which you basically just define. For example, if you have a two-parameter system, you would only define the upper and lower bounds. And obviously, if there is correlation, this shape will be changed. And in the multidimensional case, this will become a hybrid. Then once we model uncertainty in the system, so once we know whether we use a probabilistic or a non-probabilistic model, then now we can say if the input is known, the input, as I said, could be uncertain, or it could be a certain value. In any case, either when the system is uncertain or the input uncertain, one of them or both of them, you would expect that your output is going to be an uncertain variable, which have a distribution. And this is basically what we call uncertainty propagation. So once you have assigned a model to your system parameters, and once you know the input to the system, then you can propagate this uncertainty to basically calculate the outputs or the distributions of the outputs. There are loads of methods available in literature known as Monte Carlo simulation perturbation, polynomial Cayley-based inference, and it's not. I will just mention briefly about the Monte Carlo simulation later. And obviously, if you use the non-probabilistic methods, the methods are going to be different because you don't assume any PDFs. So what you have to do is basically have a hyperview view of the input parameters, and you have to map that into the space. And what we are interested in is mainly the vertices or the ranges of the variations of the outputs. And we don't assume any input. And depending on the type of the relationship between an input and output, we can use different methods. The most reliable method is optimization method, which is used in this category. But there are also other methods like parameter work exclusion if there is a monotonic relationship between input output, or sampling can be also possible. LHS. Okay, so now we come to the manufacturing uncertainty, which is the topics of our talk today. And as I mentioned before, when you have a fleet of nominally identical structures, any variability in the thickness, material properties, or joint parameters could lead to a significant variations in your results. I did during my PhD, I did develop some methods in this field, especially in terms of identification and propagation. And one of the study we did with DLR, which was published in this paper, was to show that if you have different variability like thickness materials in the parameters, experimentally we have observed that the assembling process could be the most dominant one for these larger scale structures. And maybe nowadays we can minimize the uncertainty on the system parameter, or just one piece of equipment, like one part, which is thickness of materials. We can reduce that significantly to maybe less than 1% variations, which can be then considered as deterministic if the variation is too small. But what we observe is this assembling process could change the stiffness, especially when you are joining structures together. It could change significantly the stiffness distributions of the joints, and therefore they are the most dominant source of the variability in the outputs. But the study we did with Hadi in terms of the MEMS device, we've seen that papers shown that even the uncertainty due to the geometric or other parameters could be significant, as we will explain later. It's a study done by Alexanko and his colleagues, which is shown in this paper. Okay, so I'll give you a brief introduction. After the introduction to uncertainty, I'll give you a brief introduction to microelectromechanical systems known as MEMS. You know that the MEMS devices mainly consist of small scale components, that is in nano, milli, or macro. And they can basically sense, think, and they can also communicate and act. And basically, there is a wide range of application for MEMS devices nowadays. And if you want to basically consider the MEMS is mainly consist of mechanical microstructures, microactuators, microsensors, and microelectrics in one package. So it's mainly these four components which exist in the actuation mechanisms can be via electrostatic, could be through the pneumatic, thermal, or piezoelectric actuations. And one of the very well-known phenomena is pull-in voltage, which is an instability in MEMS device. And basically, if you consider like a clamp beam here with electrostatic, and then as you apply a voltage to this system, obviously it creates a deflection, and the deflection increases as you increase the applied voltage. But it's a certain voltage that you reach to the pull-in voltage, and after that, the systems will become unstable, which is known as pull-in voltage. There are several applications for the MEMS device. So one of them is the tire pressure sensors. So they are small devices, so they don't need significant power. So the energy harvesting that we can use for these devices would be useful, especially if you consider, for example, the tire of the aircraft. The sensor location is not easily accessible, so it's important to have an energy harvesting device to power these systems. They have been actually used in also drug delivering devices for the human, and it's also used in chemical and optical applications. Now I'm going to talk about the manufacturing uncertainties in these devices. So I'll explain what I mean by manufacturing. They are going to be just aleatory uncertainty that we're going to talk. There are several papers talk about the modeling uncertainty. But you have to remember, modeling uncertainty is something we can refer as epistemic uncertainty because it's a kind of an error. So if a model is wrong, you have to change the model and choose the right model. And though, as George Box said, there's no right model, all the models are wrong. But let's say models are better representative of the physics. It's just a comparison between the models. So a study by Mirzazadeh and Marini in this work, they've done some experiments. You can see the number of samples they have is just 10, and I assume it's because producing this device, especially with the budgets you have in the university, is not feasible. They basically created 10 identical MEMS structures. You can see here is this beam with the small dimensions, thickness L. And what they did experimentally, they measured the change in the capacitance and the lower and the rotational electrostatic devices. As you can see, they applied the voltage to these two electrostatic stators, and they basically measure the change in the capacitance and due to the voltage. And you can see the variation is basically increasing as you increase the voltage. This is expected because you would have a larger deformation, and as the uncertainty effects will become more dominant as you increase the voltage. And this is where you can see the voltage is reaching to the cooling voltage. And what I want to basically say is they have shown significant variability in the capacitance. They could not really directly measure the Young modulus or geometric variations, or at least they haven't shown it in the paper. What they did, they basically mention about the sources of this geometric uncertainty, which is for example, the initial structural configurations that can be characterized by an offset. It's basically geometric imperfections, which is induced by the process of the deposition and release of polysilicon film. What they could see, this geometric imperfection could affect the gap.
Excuse me, we didn't see your. We can see your presentation. Oh,
sorry,
okay.
Sorry, it seems to kick me out of this. Is it okay now? Yeah. Okay.
Yes. Okay.
Right. Yes. So, as I said, this is basically what we observe in this paper. And what they've done in this paper, they try to estimate the variability in the geometric parameters and the Young modulus using an optimization methods. So they have the experimental model data for the all n here is 10 basically, because you have 10 samples. They have defined an objective function, which is simply the difference between the capacitance, change in the capacitance of the experimental data for each case, and the one which is created by model. And they could basically identify these parameters like Young modulus, or even the geometric parameters like O, which is shown here, which once you know O, you can determine the variation in the geometric parameters. And they observe, for example, I'm showing here the different identified values for Young modulus, and you can see that they found a mean value of 142 and a standard deviation of 10.9, and that shows basically 7% coefficient of variation. Coefficient of variation is a useful variable in statistics because it shows the ratio of the standard deviation over the mean, and this ratio is non-dimensionalized, so it's giving us an indication of the amount of variation. And you can see it's a significant variations just in the Young modulus, which is 7% variations. And that basically somehow reflected from the variations in the change in the capacitance. The other study that I have reported here is the one by Alexander, I mentioned already, Alexanenko. They also did the same thing. This time they had 12 identical devices. And they actually measured directly. They didn't use any optimization. So I would basically say their results are more reliable because they measure it directly from each devices. And you can see the pull-in voltage in this graph that for each of these cases, so they have shown, they have given numbers to each of the beams, and you can see significant variability in the pull-in voltage of each of these devices. And if these are real data, these are measured data, but it's only 12 data. They basically measure the length of the beam and they measure the width of the beam. And I basically shown here the covariance based on fitting a PDF on this data. And you can see that the covariance of the width and the length is quite small. And when they are very small, we can assume they are deterministic because the variation is negligible. Obviously, mathematicians will not accept that. As an engineer, we always define a threshold and we say any variations below that threshold, we can ignore it, okay? So that's basically what we know as an engineer, or as I said, probably not acceptable because that's not zero from a mathematician point of view. I click out again, I think. So I don't know why. Right, but when they look at the variation in the gap size, so the gap is the gap between the electrostatic and the beam. When they look at the variation in the thickness and the Young modulus, so for the gap, they found 6% coefficient of variation, 9% in the thickness, and 10% in the Young modulus. And they actually, it's consistent with the previous, the data obtained in the previous papers. That was the Young modulus reported 7%, the same amount for the geometric parameters. And now we can say these parameters can be considered non-deterministic. They use probabilistic models and to basically, I don't know why my screen is always going anyway, so they basically use a probabilistic methods to propagate this uncertainty through their model. And I'm showing just their results. They didn't look at energy harvesting, obviously. They were looking at the application of the closing time and impact velocity in their devices, and you can see a significant variations in the results. So now I come to the introduction of the MEMS energy harvester with electrostatically adjustable resonance frequency in our talk. And I'll just probably give a quick overview of different sources of the energy harvesting. Probably all the people in this community are familiar. And I'm considering only the vibration source. The device that we consider to harvest energy is piezoelectric device. And it's a beam basically with a tip mass and a piezoelectric light which can harvest energy. It's nothing surprising, and it's quite basic in this community. So it's and you assume it's subject to a base excitation, which is coming from any vibration in the real environment. And this could be, for example, due to the taxiing in the aircraft structures, or landing, or basically running down and off in the cars, or any other source of vibration in the real world. When we all know that the objective always is to have the resonance frequency of the design of your design harvester as close as possible to the frequency of the vibration source. Obviously, if you have multiple frequencies, then you basically design the system for either the multiple frequency range or for the ranges that you have the maximum power in that frequency range. And now you can see that I'm not going through all the details of the modeling. It's a little bit of the equation math here. It's basically the model Hadi developed in his PhD, which was considering a microbeam with a tip mass and energy harvesting device. Is well known to the community, and it's basically excited by a harmonic base excitation. That's basically the equation of motion. And obviously, this is coupled with the electrical equations, which is shown here. And obviously, what you can see is the tip deflection will basically occurs at the high. It's a very high frequency because it's a small size device, so it's about 96 hertz resonance frequency. And he also look at the variations of the resistance, and you can see obviously that the maximum of the power we can obtain from these energy harvesting devices basically occurs at a certain load resistance as expected. It's a very small amount of power that can be harvested, and obviously because it's a MEMS device, so the order of the power we gain is in nanowatts. The main motivation that Hadi was following was to say that, okay, if there is a variability in the system parameters, how can we adjust the resonance frequency in order to basically match the frequency from the excitation to maximize the power. So the idea that we used was, okay, many MEMS devices use electrodes. As I said, different applications for the electrodes is switching up, down, and often other applications. Our application was to see whether this can be used for adjusting the resonance frequencies. So we started with this concept that, okay, we have the same microbeam subject to the harmonic excitation. It's basically attached with the two layers of the piezo, and this is the electrical circuit here. And what we have in addition to the previous equation is additional force due to the electrostatics, because these two surfaces are the electrodes and they basically create a force. And this force can be basically modeled in the equation of motion as an external force into the system. It's a function of the applied voltage. So as you change the voltage, this force will be changing, and it's also a function of the distance between the beam and the electrodes. And because the beam is vibrating, therefore this distance or gap will be also changing. Again, recall that in the previous experimental measurement, they've shown significant variability in this gap when it comes to the manufacturing process. And this gap is one of the difficult ones which they can produce it with a precise number. And what we can represent this electrostatic nonlinearity with these equations, as I said, it's inversely proportional to the displacement. This W is basically the deflection in your beam, is basically deflection. Obviously, when the beam goes down, the distance between the electrode 2 and the beam is G0 minus W, the tip deflection. And we have used it in a symmetric way. And the main reason that we use it in a symmetric way in both sides was to basically simplify the equation of motion. Because when you expand this in using a Taylor series, you only have the odd terms in the nonlinear terms, right? And then normally from nonlinear dynamics, the solution of the nonlinear system with odd terms would be probably, we can use more efficient methods to do that. And then if we are only exciting it with a single mode, obviously we can use the Galerkin to project the system to the mode shapes. That is that is the one that is basically exciting the system. And you can basically reduce the order of the partial differential equation to a single nonlinear DOF systems with a number of terms which is retained from the electrostatic force. Obviously, there is a question is how many terms have to be retained, and that's a interesting and a challenging question. What we did is we normally consider a convergence study in order to see how many terms would be enough in order to to basically capture most of the behavior of the system. So some results here. I mentioned about the pulling voltage. So, for example, this length refers to the length of the piezoelectric materials. We obviously want, if you are just exciting the first mode, so ideally we would like the length of the piezoelectric to be as high as possible, ideally the whole length. But the problem is, as you increase the length, you have to reduce the pulling voltage, right? So you can see the difference between when you have only 20% of the beam covered by piezo, the pulling voltage is about like 17, 18. When that is increased to 50%, the pulling voltage decreases to 14 or 13. But the thing is, if you have the gap is also another parameters which affect your pulling voltage. Obviously, you would expect as you decrease the gap, the pulling voltage increases. But remember, the gap is something that we give us the opportunity to apply more forces to the system by applying voltages, so you can have a wider range of frequency range, as I will explain later. But as I said, everything is limited by the pulling voltage, that we cannot increase our system parameters to any values that we want. What we could observe is that when we basically perform a convergence study on the number of terms that have to be retained in the analysis, we have used harmonic balance methods. And you can see that the results are changing as we increase the number of terms, but it reached to almost same curves when we include the ninth order. And that was the conclusion that we say, okay, ninth terms would be enough for the analysis to see. And then we also compare that with the numerical results. With the numerical results, you don't need to do any truncation. You can apply the force directly, but obviously you cannot obtain these unstable branches. But we could see that is a quite accurate result. So it shows that any nonlinear terms beyond ninth order can be neglected in our analysis. And we did a study on the operational range of frequencies, and you can see when we don't apply any voltage to the electrostatics, this is the frequency range. And by applying voltage, we can see that the resonance frequency will increase, although the level decreases. But still, if you compare, for example, these values at the 4-volt electrostatic here, is quite higher than the case when we don't apply any voltage. And I'll explain later that voltage is not an additional energy we put in. It can be actually gained from the change in the capacitance. Obviously, there would be some loss, but I will show later, because the first question which can arise is, okay, you apply a voltage to the system, this means you put energy into the system. So you're saying that I gain energy, but what is the balance? But I'll explain later that that energy will be basically covered from the change in the capacitance of the system. So what we can see is that the range of the power that can be basically obtained by applying voltage in here. And obviously we are limited with the pulling voltage. So anything above 12 volts is close to pulling voltage. We have to actually have a safety margin as well. And with the length, change of the length, we can again see that the voltage you need is less as you increase the length of the piezo. So these are some observations in our systems. So this concept of using electrostatic devices for changing the resonance frequency can be used when we consider the effects of manufacturing uncertainty in MEMS energy harvester. So I already mentioned that there are different sorts of manufacturing uncertainties in the MEMS devices. They are listed here. I don't need to explain again. What we did, we used the data from reference 2, which I mentioned that the thickness, air gap, and Young modulus, these three parameters were the one which has the highest coefficients of variations. And we include them as the uncertain parameters in our model. And we could basically plot the PDF. We use a probabilistic model, so we assume a normal distributions for these three parameters in the system. And we use basically a probabilistic methods known as Monte Carlo simulations. I'll explain about Monte Carlo simulation later. It's one of the uncertainty propagation methods. And obviously it needs a large number of samples in order to obtain the PDF and the outputs of the system, which could be resonance frequency or the power, which is shown here. We did a convergence study on the Monte Carlo simulations. When we increased the number of samples from 1,500 to 2,000, we observed that the change in the distributions of the PDFs is not changed. So we concluded that 2,000 samples will be enough to estimate the PDFs of the outputs in this system. So based on that, you have to consider that we give a nominal design to the manufacturer. So we say, okay, we want an energy harvesting device with these nominal geometric and material parameters. And as I mentioned, when it goes to the manufacturing mass productions in the by the manufacturers, you would expect tolerances. And I mentioned that these tolerances could be much more significant in the MEMS scales compared, because when we talk about the larger scale structures, this uncertainty can go down to 3–4% in the worst case scenarios. But in the MEMS scales, these are about 10%, which are quite significant variability. And it could basically affect significantly the performance of your device. So based on this idea, we can say that when we give the nominal values, which is basically assign a resonance frequency, then anything comes out from the production line could have either a higher or a lower resonance frequency compared to what we have given as the nominal design. So in this case, you would need two mechanisms. One is that you can increase the resonance frequency, or you can decrease the resonance frequency. So that's basically the two ways. So what we did, in addition to the two electrodes that we had in the previous system, we use another arc-shaped electrodes that you can see here. And we can say we apply voltage 1 and 2. The arc shape is basically creating a compressive load and increase the stiffness, and as a result, it increases the frequencies. On the other hand, the lateral electrostatic panels will basically reduce the resonance frequency. And then in this case, we can have the advantage of increasing and decreasing depending on the parameter variations. And the fourth one is basically represented as the one that we just explained in the previous design. And obviously the second one, as I said, it creates a positive stiffness and it increased the stiffness. And we can include them in the equation of motion. Obviously the axial force created by this electrostatic will appear in the equation of motion here, and F2 and F1 are calculated using these two equations. And F2 will not create any nonlinearity. It's going to be a linear stiffness. And it's a bit challenging to solve this problem, especially we have nonlinearity in the system, and at the same time we want to do a stochastic analysis. So in a way that it's a stochastic nonlinear systems that we want to basically consider. And the methods that we used to solve the nonlinear system was called shooting methods, that the scheme is shown here. And basically with the shooting methods, we create a large number of initial guesses of the initial conditions, and we use the Newton-Raphson methods to basically predict the solutions. The main reason that we use this is basically we wanted to create a most efficient methods for the nonlinear solution, and we use these methods and solve the problem. And you can see, for example, in this graph that by applying the voltage, for example, to the lateral electrostatics, we can see that the resonance frequency moves to the back. And in here, by applying voltage, we can see the resonance frequency increases to the right. And this is what we know as hardening effect, and this is what we know as softening effect. What is interesting about this device, especially with the lateral electrostatic, is that there is always a question that nonlinear community could ask, and that's basically it's not really stable to always stay at the higher branch, and always when you are at this branch, it's very likely that you basically jump to the lower branch. And that's quite an interesting question. And basically what we have seen with this device is that actually this voltage can be used in order to bring us back into the higher branch. And how we can do that? So imagine if we apply a voltage 8 to the system, and we are located at this point. And so for any kind of change in the initial conditions, it drops to the lower branch. Then what you can do, you can increase the voltage from 8 to 18 until you come to the stable branch of the 18 volt. And then you can gradually, incrementally, or very slowly increase the voltage to bring the system back into the higher branch. So that's basically what you can also see in the system. So that's one of the also interesting observations from this device that we've seen. And then I mentioned that in addition to the shooting methods for solution of the nonlinear system, for every time you also need to do a Monte Carlo simulation, which this flowchart shows the Monte Carlo simulation. It's the simplest methods for uncertainty propagation, but obviously it's very time consuming. And one of the future studies that we're interested in is to basically solve this problem in a more efficient way. The idea is you have defined a PDF for the input parameters. You generate n number of samples, and by assuming, for example, the PDF in the system, you just do a single deterministic analysis. In this case, for each case, among those 2,000 cases, we do a nonlinear solution using shooting, and basically we extract the responses. And the convergence study that I mentioned is basically defined on the case that when you see the PDF or the histograms of your outputs will not change as you increase the number of samples. And then in that case, you can say convergence achieved, and you can compute the statistics of the response. So this is just some results on this system parameters. So if you don't apply any voltage and considering the same amount of uncertainty in the system, so we can see the PDF of the harvested power. In majority of the cases, we have very low number as expected because you are away from the resonance frequency. So you have a very large variations in the harvested power. And if you assume this is a device which is going to be in the real application, you can see that although you have expected a mean value about 0.2 nanowatt, for example, for your energy harvested power, but in reality, many of the samples which came from this production line will be located on the low values of the power. And when you basically apply the voltage, to the system, you can see that not only the variation will reduce, but also the amount of power will be considerably higher in most of the samples that we consider. And that's for the softening effects when you apply V1, and that's for the hardening when you apply V2. And this is basically what also shown in the two-dimensional case for the power. Okay, so I'm coming to the end now. I mentioned about the question, what will happen with the voltage that we need to apply to the system? So that's also an interesting question because you say, okay, we gain some power, but where this energy comes from? Just briefly mentioning that that will come from the change in the capacitance of this electrostatic. So basically, you can say the charge is capacitance times voltage. If you have a constant voltage applied to the system, obviously, as you decrease the distance between these two electrodes, you basically increase the capacitance and you can create charge, and that charge can be used to basically for the other capacitance. So that's somehow the energy harvested from this electrostatic device can be used in order to keep the voltage constant in the system. And then for the case of the hardening effect, what we can say is the power loss of the voltage source V2 is too small. It's mainly because we have an axial deformation of the beam, which is negligible compared to the deformation in the lateral direction. So that brings me to the end of my talk, 50 minutes planned, and it's basically we studied the manufacturing uncertainties in MEMS, and we have actually reported the significant effects of the manufacturing uncertainties in MEMS devices. What we have shown in these two basically initial studies, I would call them, is that some basically methods are required to minimize this effect when it comes to the production line. Okay, so we have used the electrostatic device to do this in the MEMS device, but in reality, you always have these manufacturing uncertainties, and it's always important to also come up with different ideas in order to adjust these any variations in your system parameters. In the future work, we haven't obviously a budget to do experiment. As I said, anything with the MEMS is expensive, and it needs, especially when we talk about the uncertainty, then we need a kind of a reasonable amount of samples in order to manufacture. And experimental facilities also could be expensive, but both of these concepts could be interesting for the future studies. And on top of that, the MEMS devices are mainly nonlinear, and when you add uncertainty to this system, then you have a stochastic nonlinear model. So it's important to again develop efficient methods in order to solve. There is a large amount of papers and efforts in the last 10 years on developing efficient methods for the stochastic linear systems, but I think there is kind of a not significant amount of work for efficient methods for nonlinear, and I can understand it's quite a difficult subject to handle. So that's about me. Thank you very much for your attention. I hope you like my talk, and if any questions, I'm happy to take. Thank you.
Thank you very much for this interesting presentation. I think that now the session is open for questions, so you can all of you